and welcome to the fourth part, which is the last part of our topic on Strand 3.1. Today we are going to be studying about the topic on electrochemistry. Electrochemistry is a study of electricity. So we are going to be studying about how electricity can be produced by bringing about chemical reactions. Electrochemistry is all around us. So when we look at any gadget which contains a battery in them, that is an electrochemical cell. Gadgets such as cell phones, computers, laptops, and even in a human body. Human body contains an electrochemical cell because the chemical messages that are traveling down the neuron, they are electrical in nature. Okay, so gadgets like cell phones, like I said, hearing aids, watches, and many more. These are all containing batteries in them. They are battery operated gadgets where the chemical energy in the battery is converted into electrical energy. Now, whenever electrons move around in an external circuit, electricity is produced. In electrochemistry, the movement of electrons that generate from one species that is getting oxidized and then moving into the other species which is getting reduced and in turn producing electricity is called electrochemistry. So basically, electrochemistry uses the concept of moving electricity or producing electricity from a chemical reaction. The opposite of electrochemistry is electrolytic cell, okay, or electrolysis. Electrolysis uses electricity to bring about a redox reaction. So let's look at the difference between the two cells. In the electrolytic cell, the anode is positive, while in electrochemical cell, the anode is negative. Both of these have oxidation happening at the anode, okay, regardless of the fact that one is a positive and the other is a negative. Then in the electrolytic cell, the cathode is negative, and in electrochemical cell, the cathode is positive. Again, regardless of this, both of them have reduction happening at the same time and the same electrode. Then in the electrolytic cell, which is causing electrolysis in the reaction, it is using the energy conversion from electrical energy to chemical energy. So here electricity is used to bring about a set of redox reaction in the cell, while the electrochemical cell is using chemical reaction, that is chemical energy, to produce electrical energy. And then in the electrolytic cell, both oxidation and reduction happen in the same cell, while in electrochemical cell, the two cells are separated by a salt bridge. A salt bridge is an external device or an external piece of glassware that is connecting the two half cells together. This salt bridge is containing an ionic solution, and this ionic solution can either be potassium nitrate or potassium chloride. So a tube is filled with this solution and then they are plunged into the two half cells. The purpose of the salt bridge is to make sure that no precipitation reaction takes place in either of the half cells. The other very important function of the salt bridge is to keep the cell electrically neutral. What it basically means is that if one of the cells is having an extra buildup of positive ion, then the negative ion of the salt bridge will come down and compensate for it. On the other hand, if there is an excess buildup of negative ion in any of the half cell, then the positive ion from the salt bridge will come down and compensate for it. So this is how the salt bridge keeps the cell electrically neutral. So when reactions take place in electrochemical cell, one cell is having an oxidation reaction while the other one is having a reduction reaction, both of which are separated by a salt bridge. So if we have to summarize the reactions down, it is going to be written in a cell notation summary. Let's have a look at one example. In this example, there are two half cells which are separated by a porous disc, which is the salt bridge. So in one half cell, the zinc is oxidizing to zinc ion, while in the other one, the copper ion is reducing itself to copper. So if we have to write a summary for these reactions happening in the cell, this is how it will be written as. It explains is this, that on the left hand side is always the oxidation cell right hand side is always a reduction cell. Okay, then we can see that zinc is changing into zinc ion. Here zinc is acting as an electrode and zinc ion is in the solution, which is aqueous form. So both of these states or phases are separated by a single slash. We write the slash like this. Okay, we have an inclined slash. So we will have the electrode oxidizing into the electrolyte, and that is the order we write, separated by a slash. Now the two half cells are separated by a salt bridge, which is a double slash. And then you can see on the right hand side, the conversion is from copper ion to copper. That means copper ion is reducing itself to copper. Again, the two phases are separated by a slash, okay, which is this slash here that we have learned. So just a summary as to how we are going to go about doing the calculation in electrochemistry. The whole reason as to why we are learning this particular session is so that we are able to calculate the EMF, which is the electromotive force of the particular cell. Remember, we said that electrochemistry involves the conversion of energy from chemical to electrical. So when electricity is produced, we need to know what is the voltage of the current. Okay, so this is how we work this out. The EMF of the cell, if it is a negative value, then what it basically means is that the cells are positioned the wrong way. What it means is that the left cell would be positioned on the right hand side and the right would be positioned on the left hand side, vice versa. Okay, so if that is the case, then we will have to switch them around. The negative EMF value will also indicate that the particular reaction to which the negative value has been derived does not take place in reality. When the E naught or the EMF of the cell is a positive value, then it basically means that the cell is going to operate. Okay, that means the cell is positioned in the right way. When a cell reaction takes place or when a reaction is possible, we use the word spontaneity, or we say the reaction is spontaneous. So this is how we calculate the E naught of the cell or EMF of the cell by using the formula. The electrode potential value on the right hand electrode minus electrode potential on the left hand electrode. Right is always reduction cell, left is always oxidation cell. So the electrode potential of the reduction minus electrode potential on the oxidation will give you the electromotive force of the cell. And to add it up, we can say that to find out what reaction is happening on the right hand electrode and what is happening on the left hand electrode can be determined by looking at the magnitude of the electrode potential value. If the electrode potential value is more negative, it simply means that the cell is containing a reducing agent. If the cell contains a reducing agent, that cell will be the oxidation cell. If the electrode potential value of a particular half cell is more positive, it means it contains an oxidizing agent. That means that is a reduction cell. So this is the part we have to remember in order for us to solve the problem of calculating the EMF. Now, before we learn how to do the calculation of the EMF of the cell or how we are using the electrode potential value to predict certain reaction, let me look at one application of this. We are given the electrode potential values of three half cells, a zinc cell, Fe cell, iron cell, and the copper cell. So if we have to coat iron with zinc in order to prevent it from corrosion, how will the reaction happen and what is going to happen in the scenario? Now in this case, iron is a very less reactive metal while zinc is a very reactive metal compared to iron. So coating a more reactive metal to iron, will it prevent corrosion or will it cause further corrosion? Let's use this electrode potential value to find the answer to this. So when we have iron and zinc, let's compare the electrode potential values of these two half cells. Now the cell that contains a more negative electrode potential value, we said, is containing a reducing agent. So we say that is our oxidation cell. So in this case, the more negative magnitude of the value, okay? So the more negative value is 0.76 volts, negative 0.76 volts. So that will be our oxidation cell. So out of these two chemicals, zinc and zinc ion, it is a zinc that is going to get oxidized. So when zinc is oxidizing itself, then Fe2 plus, which is in the less negative electrode potential value, less positive or less negative electrode potential value or more positive would mean it contains an oxidizing agent, anything getting reduced. So that is why Fe2 plus is the one that is going to get reduced. So it basically means that zinc is going to get oxidized into zinc ion, while Fe2 plus is going to change into Fe. So when this reaction happens, then it is the zinc that is going to corrode, not the iron, because iron cannot change into Fe, cannot change into Fe2 plus. It is Fe2 plus that can change into Fe. Only forward reactions are possible. Backward reactions are not possible. Okay, so when zinc is changing into zinc ion, the zinc is going to corrode, while the tin on which the galvanized nail has been applied to is going to remain, okay, is going to remain intact. It's not going to corrode. We're going to look at another scenario where instead of zinc, we are putting copper. So we are coating copper with iron. Let's see what is going to happen. Copper is less reactive than iron. So if we use a less reactive metal to prevent a more reactive metal from corrosion, is it going to work out? Let's find this out. Again, we compare the electrode potential value of the two cells. Now here, the more negative value is the iron cell. So more negative means it contains a reducing agent, anything getting oxidized. So out of Fe and Fe2 plus, it is the Fe that is going to get oxidized. Then the more positive electrode potential value will indicate an oxidizing agent. That is our reduction cell. So oxidizing agent is anything getting reduced. So between copper and copper ion, it is a copper ion that is getting reduced. So the reaction that happens is Fe will oxidize to Fe2 plus. The copper ion will reduce itself to copper. So if you coat copper on top of iron, will the iron be prevented from corrosion? Definitely not, because when this combination is used, it is the iron that is going to corrode. That means iron is the one getting oxidized. And when iron is corroding, then you can see the rest of the material is also corroding with it. While the copper, which is on the nail, doesn't corrode. This kind of corrosion prevention is known as a sacrificial corrosion. Okay, sacrificial corrosion is where one metal is sacrificing itself to corrode in order to protect the other one from corroding. So in the first case, it is a zinc that is sacrificing itself. Zinc is oxidizing itself in order to protect the iron from corroding. While in this case, that's not happening. Okay, so instead of protecting the iron from corroding, it causes a combination with iron and copper causes the iron to oxidize. So this is one application of electrochemistry. It allows us to understand better why certain metals are able to react and also why certain substances are not able to react with the metal. Okay, so all these things have to do with the electrode potential value of the individual half cell. Next, let's look at one example and see how we can use electrode potential value to make a prediction about this particular reaction. So electrode potential value basically is used for two important things. It is used to predict whether a particular reaction is going to happen or no, and it is also used to calculate the electromotive force of a particular cell. So we are given two combinations. We have the magnesium cell and the lead cell. We choose the one which is the more negative one, and the more negative one again contains a reducing agent, anything getting oxidized. So we are going to be looking at two different methods as to how we can solve this problem. Okay, let's look at the first method. The first method, we identify the chemical that is undergoing oxidation, and that chemical will be the one carrying the most negative E0 value. So that's magnesium getting oxidized. Okay, so we have the reaction of magnesium oxidizing itself to magnesium ion. And then we have the less negative. The less negative or more positive will be our oxidizing agent. Anything that is getting reduced. So between lead ion and lead, it is the lead ion that is getting reduced. So lead ion reducing itself to lead metal, and then you can balance the equation by putting the electrons. Write the overall equation. Okay, to write the overall equation, we will cancel the we have learned in our earlier session of writing balance equations. So when the electrons are cancelled out, this is what we get. So what does this equation actually mean? This equation means that forward reaction is possible, not the backward reaction. So it basically means that it is a magnesium that can react with the lead ions. Magnesium ion cannot react with lead metal. Okay, so that is the reason why lead in comparison to magnesium is far more unreactive or less reactive. Magnesium is more reactive than lead because of its electrode potential value. It is more negative. So this is the conclusion we can make. Magnesium can react with lead ion, okay, which is coming from the lead nitrate, as both these substances appear on the reactant side. So this is one way in which we can answer this particular question. Will magnesium react with lead nitrate? And we have done that by noting down which chemical is getting oxidized and which chemical is getting reduced. So one more time, magnesium was getting oxidized, so this is our strong reductant. Okay, while lead ion was getting reduced, so this was our strong oxidant. The other method that we use is to calculate the EMF and see if the EMF comes to a negative value or a positive value. If you recall the table which I showed you, the flow chart, if the EMF of the cell is negative, it basically means that that reaction doesn't happen. But if the EMF of the cell is positive, it means that reaction is possible. So what the question is asking us is magnesium going to react with lead nitrate? So this is the reaction that we have to answer. Will magnesium react with lead ion? Okay, that's what we have to find out. According to this reaction, magnesium is getting oxidized and lead ion is getting reduced. So let's use this concept to calculate the EMF and use this formula now. EMF is equal to E naught, which is electrode potential on the right hand electrode, minus electrode potential on the left hand electrode. Right is for reduction, left is for oxidation. So reduction one is a lead ion, and the lead ion electrode value is negative 0.13, minus magnesium, which is oxidation, is minus 2.36 volts. So when we do this maths, we will have our EMF as a positive value, positive 2.23 volts. So if the EMF is a positive value, it means that this reaction is spontaneous. Okay, and this is how we write it as. Yes, the reaction is spontaneous because the EMF is positive. So both these methods actually answer the same thing, but you can decide which one you are going to use when you have this kind of questions. We look at some more examples. And in this example, we will be predicting if zinc is going to react with silver nitrate. Silver nitrate contains silver ion, so we'll have to keep that in mind. So I'm going to use the EMF method to find this answer to the question. Now, if zinc is reacting with silver nitrate, our equation expected is this. And this is how we will expect our equation to appear. Zinc plus silver ion. Is this reaction possible or no? According to this reaction, zinc is getting oxidized, silver ion is getting reduced. So let's calculate our EMF. The electric potential on the RHE, which is the right hand electrode, is the silver ion, which is 0.80 volt. The E naught on the LHE is the electric potential on the oxidation cell, which is the zinc cell, that's negative 0.76. Put that in the equation and this is what we have. The EMF comes to a positive value. So the EMF comes to a positive value. It basically, this reaction is possible. And according to this reaction, zinc can react with silver ion, but silver cannot react with zinc ion. The backward reaction is not possible. So the answer to this question, when you write it, this is how it will be. Yes, the reaction is spontaneous because the EMF of the cell is a positive. Let's look at another example. Here we want to find out if copper reacts with silver chloride. So we have copper plus silver ion that's in silver chloride. Is this reaction possible or no? This reaction, copper is getting oxidized while silver ion is getting reduced. Okay, so let's use the electrode potential value of the reduction half cell of silver and the oxidation half cell of copper. So when we calculate the EMF, this is what we get. A value comes to positive. Again, we can say that the cell reaction is possible, meaning copper can react with silver ion, but silver metal cannot react with copper ion. Okay. So after we understand the importance of the inner terms of the cell or the electrode potential of a particular half cell, we will now learn what is its significance to the reactivity of a substance. Okay, so we can say that the electrode potential value will tell us whether a particular metal is more reactive or less reactive. And we can do that by comparing their electrode potential values. Like we said earlier on, if the electrode potential value is more negative, it means the chemical is getting oxidized. So it's a reducing agent. If the electrode potential value is positive, the chemical is getting reduced. So it is an oxidizing agent. Now those metals which have low ionization energies, this simply means that these metals need less energy in order for them to remove the electron in their last orbital. Okay, so in order to remove the last electron, less energy is required. That's why the ionization energy is low. So when a metal can easily lose an electron using less energy, we say that that metal is very reactive. The highly reactive metals will have a large negative electrode potential values. So we say that these metals which have high reactivity, they have a greater negative electrode potential value. They are very good reducing agents because they get oxidized. So in contrast, if a metal is having a positive electrode potential value, what does it mean? A positive electrode potential value will indicate that the chemical is getting reduced. Okay, so if the chemical is getting reduced, it simply means it is acting as an oxidizing agent. Metals always oxidize when it has to react with a particular substance. If a particular metal doesn't oxidize, we say that it cannot react. So a positive electrode potential value simply means that this metal cannot oxidize itself. Therefore, they cannot react with acids. Okay, so let's compare this with the metal which has more negative electrode potential value. A metal which has more negative electrode potential value can easily oxidize itself. That means it can easily react with other substances like acids. So when we compare the reactivity series of the metal, this is what we get. All the metals in the reactivity series, they will carry a more negative electrode potential value. That means these metals are easily oxidized. But then these metals which are right at the bottom here like copper, silver and gold, these metals will have electrode potential values in positive. That means these metals cannot oxidize. In other words, they cannot react with an acid. When we compare the metals to a non-metal, non-metals mostly have positive electrode potential values because non-metals always reduce themselves. So when a non-metal is reducing itself, we say they are oxidizing agents. Okay. And one example we can see is here. A metal will oxidize itself by losing an electron. So the electrode potential value of this metal will be negative. On the other hand, you can see that here a non-metal is reducing itself. When a non-metal is reducing itself, the electrode potential of this non-metal will be a positive value. That is why this reduction reaction is possible. So basically, to sum it up, we can say that electrode potential values are very good indicators of a metal reactivity to compare whether a particular metal is more reactive or less reactive. Okay. Finally, let's answer the basic question. How are we able to determine the electrode potential value of a particular half cell? To do that, the usage of standard hydrogen electrode is used, okay? And the abbreviation for that is SHE, that's She for short form. So what this basically does is this electrode, this hydrogen electrode is a standard electrode. It's a reference electrode that is used to measure the electrode potential of any half cell. Okay, let's say for instance, when we are calculating the electrode potential value of a copper half cell. Copper half cell's electrode potential value is a positive 0.34 volts. So how did the positive 0.4 volts come up? Experimentally, the reference for this potential of the hydrogen electrode is a 0 voltage, and this reaction is carried out under standard conditions of 1 mole per liter solution concentration. The pressure has to be 1 atmosphere and the temperature will be 298 Kelvin. Under these three standard conditions, then this standard hydrogen electrode can be used. So this is how the standard hydrogen electrode looks like. Now this standard hydrogen electrode will be connected to the half cell whose electrode potential we are interested in finding. So if we connect these to a copper half cell, there will be a flow of electron, there will be a redox reaction carried out here, and the voltmeter reading will tell you the voltage of the half cell for copper. Like I said, the voltage, the electrode potential voltage for copper is 0.34 volt. So this is what we have when you round it off. Okay. So students, I hope you have understood about electrochemistry. The important thing you have to know about electrochemistry is the differences between electrolytic and electrochemical cell. You need to know how you can use the electrode potential value to predict a particular reaction, and also how to calculate the EMF of the cell. Moreover, we have learned the relationship between electrode potential value and the reactivity of a metal. So you have to go over that as well. And also how we use the standard hydrogen electrode to calculate the electrode potential value of a particular half cell. Until then, I'm going to take leave, and we will see you in the next strand, which is strand 3.2. Take care, students. Bye.